This is a video for MEI Core Pure Mathematics, complex numbers 5, complex roots, 5.2, the nth roots of unity. You've seen that when n equals 3 and when n equals 4, the roots of z cubed equals 1 give you 3 roots spaced evenly around a circle, and when n equals 4, you get 4 roots spaced evenly around the same circle, radius 1. We've also seen that the roots of unity all lie on a unit circle, whatever the power, with one root at 1. So because the mod of z to the n is equal to 1, every root of the equation z to the n equals 1 must have a unit modulus. And this means that every root can be written in the form z is equal to cos theta plus I sine theta. So if z to the n equals 1, that means that cos theta plus I sine theta to the n equals 1. And using de Moivre's theorem, that gives us that cos n theta plus I sine n theta is equal to 1. And that tells us that n theta must be 2k pi. If we look at this plot over here, we can see that I've got n equals 6, so I get 6 roots spaced evenly around the unit circle. And each of these angles is the same angle, it's pi by 3, or if you prefer, it's 2 pi by 6, which we will have picked up from here. The k value referred to can be 0, that would put it here, or 1, 2, 3, 4, and 5. If I change the value of n, then I just up the number of solutions, and therefore I get an increase in the number of points around the circle. So if I go up to 15, you can see I get 15 roots for z to the 15 equals 1. So the equation z to the n equals 1 has exactly n roots. They're all of this form, cos of 2k pi by n plus I sine 2k pi by n, where k is an integer between 0 and n minus 1. In fact, if k is larger than n minus 1, for instance, if it was n, then if you think about this here, it will become 2n pi over n, or just 2 pi, and so you'll start to get a repetition of each of the roots. If we look at this diagram over here, we've got the 6 points. This is k equals 0, k equals 1, 2, 3, 4, and 5. These roots are called the nth roots of unity and always include z equals 1, that's when k equals 0, and they always include a z equals minus 1 provided n is even, and that will happen when k is equal to n over 2. So in our example, we've got 6 roots and we get our minus 1 root at k equals 3. We use the letter omega for the root with the smallest principal argument, so it would be this one. So by de Moivre's theorem, we get that omega to the k is going to be cos of 2k pi by n plus I sine 2k pi by n. So the nth roots of unity can be written as a sequence 1 omega all the way up to omega to the n minus 1. And we've already seen they can be represented on an Argand diagram as vertices of a regular n-sided polygon. This is the Argand diagram for n equals 8. So omega would be the first of those, the one with the smallest argument. So this would be omega squared. Remember, multiplication is multiply the moduli, add the arguments, so it's still going to be on the unit circle, and it will be 2 sections around. So this will be omega cubed, omega to the 4, omega to the 5, omega to the 6, omega to the 7, and of course we always get 1. You can think of that as omega to the 0 if you prefer. So what about the sum of all the nth roots of unity? Well, it's a geometric series. We've got 1 plus omega squared. So we've got a first term of 1 and a common ratio of omega. Well, the sum for that is going to be 1 times 1 minus omega to the n, there it is, divided by 1 minus omega. But that's equal to 0 because we know that omega to the n is equal to 1. So if we add all of our nth roots of unity together, whatever the value of n, we will always get 0. The next video in this sequence is 5.3, the nth roots of any complex number.